Today, we want to continue our investigation of what will soon be our favorite technique of integration, and that is trigonometric substitution. There are three phases of trigonometric substitution that we have to become familiar with. The first phase, the substitution itself. That's what we talked about in part one with the tangent case, the sine case, and the secant case. This will take our x integral with that some quadratic form and turn it into a theta integral, which is most often going to be the product of powers of trig functions that are not substitution integrals. This opens up two possibilities: even powers of cosine and odd powers of secant. Specifically, we have even powers of cosine without any sines, specifically any odd powers of sine. And odd powers of secant, specifically without tangents. In particular, without odd powers of tangents. If we have even powers of cosine with an odd power of sine, that's just substitution. If we have odd powers of secant and an odd power of tangent, that's a substitution. So specifically, we're going for not substitution. And there are just these two categories: even powers of cosine, odd powers of secant. Those are the integrals that we need to learn for trigonometric substitution. First, actually, probably second. Second, we need to learn the technique for each of these. In the category of odd powers of secant, we're just going to use parts. Plus our memory. The technique is going to be parts, but at the core, we're going to have to know some odd powers of secant without technique. For even powers of cosine, we're going to use double angle identity. That's going to be our technique. Even powers of cosine can also be done with parts. We can also use parts, but this gets excessive. It gets extra messy for higher powers of cosine. I'm just going to leave it at, you could also use parts. And I'm going to try to convince you that just using a double angle identity is superior. Actually, I'm not going to try to convince you that. I'm just going to show you the double angle identity and theorize that you are probably going to prefer it. Addendum to that, you prefer just to look stuff up on Wolfram Alpha, but that's clearly not our plan. The other thing that we have to deal with is, why do we only care about these products of powers of trig functions? If your theta integral in this process, specifically in trigonometric substitution, if your theta integral is substitution, your original x integral was substitution already. Stop, go back, and find that substitution. If your theta integral ends up being substitution, for example, an odd power of cosine, stop. Your original x integral was substitution. Stop doing trigonometric substitution. Go back and just do substitution. I'm not saying that it wouldn't work to continue doing trigonometric substitution, but you're making the problem way more complicated than you need to make it. And at this point, you are less than halfway, so rounding says go back. That's just how rounding works. If you are not past halfway, stop, go back. And once we look at our theta integral, we say, hey, this is substitution. We need to stop, just go back to what we started with and look for the substitution that was already in play. Let me give you an example of something that is obviously substitution. And let's pretend that we don't notice and try to do trigonometric substitution. All right, so here is a nice obvious substitution problem. If you don't recognize this as obviously substitution, then you need more training on substitution. We're going to pretend that we don't notice, because this is what happens in Calc 2. I talk about all these techniques of substitution, and then the first test shows up, and I put this problem on. It's like, I'm going to give them a nice, easy integration by substitution. And as soon as I'm like, 9 plus x squared, that's a tangent case. And I'm like, whoa, hold on, what are you doing? And you're like, trig sub. See, that's why I can tell it's everybody's favorite. Because you just start overdoing the problems, like immediate. Let's find out what happens. So let's pretend that we just missed out on the substitution. We didn't notice that there is an x squared and the x in here. There's going to be a 1/2 and then w to the 1/2. So let's just overcomplicate things. We're going to be like a tangent case of trigonometric substitution, because fuck yeah, trigonometric substitution. Oops. We're going to make x, excuse me. That's how much I really want this to be just regular substitution. But here we go. We're pretending. If we do the substitution, x equals 3 tangent theta, then I'm going to need to replace the dx as well with a 3 secant squared theta to theta squared. Now, when we go to make our substitution, all the x's have to be converted into thetas, including this x out in front that we're conveniently ignoring. Not completely, we're still going to replace it with 3 tangent of theta. Because we know that we have to replace all the x with our theta. As soon as we finish our substitution, then we do the thing that we're doing this for. The whole point of the exercise. where the 9 plus 9 tangent squared theta becomes 9 secant squared theta. Two terms become one term through a Pythagorean identity. That was the point of the trigonometric substitution. This is the reason that we're doing this. So I still got this 3 tangent theta. That was the x that we're not noticing is supposed to be the dw. We have a square root, and now our square root applies not to 2 terms, but 1 term. Same plan that we had yesterday. Now that the exponent, that radical, applies to just 1 term, I can distribute the radical to the factors in that product. So the square root of 9 secant squared theta is 3 secant theta. Now I'm going to put this all together. I've got 3 times 3 times another 3. I've got a 27 that I'll pull out in front. And I've got tangent and secant cubed theta. Now, this is an odd power of secant, but it also has an odd power of tangent. And so at this point, we recognize a substitution. It's not just an odd power of secant, this is an odd power of secant with a tangent. So I can do a substitution. I can let W equal secant and my dw can be secant tangent. At this point, we recognize that we are doing a substitution on a theta integral in a trigonometric substitution problem. So we have to stop and say, hang on, if I'm doing substitution now, I should have been doing substitution before. So we're going to abandon this whole thing and go back to our original problem and make the proper substitution. Oops. Let's say go back and find the easier substitution. I like it that phrasing. That phrasing better. Once we recognize that we're doing a substitution inside of another substitution, we got to stop and go back and find a simpler substitution. Don't do substitution inside a substitution. There was a better substitution at the beginning. So we go back to the beginning and say, this was not the way. We should have done W equals 9 plus x squared. And then dw is 2x to x. it's fine to do parts inside of parts. It is not okay to do substitution inside of a substitution. If you're in the middle of a substitution, you're about to do another substitution, stop. Go back and find a better substitution. Not because it won't work, but because you're doing too much work. Every time you add one more step that you're writing down, every time you have to take one more step in a math problem, you are increasing the likelihood that you mess it up and end up in a bad place. Any questions? Trying to reduce the amount of writing that we do. You're in a math class, so you can stop doing all the friggin' math. So like I said, this substitution will work perfectly fine on your theta integral. And even though we don't know how to undo the substitution in a trigonometric substitution, when we undo it, it'll work out just fine. But we don't want to do that. We want to go back to our original. Question? How's everybody okay? All right. So that's thing number one about this integration phase of trigonometric substitution. Remember, trigonometric substitution has three phases. The substitution itself, with one of the three cases. Now we're looking at the integration step, where we're integrating products of powers of trig functions that are not substitution. That means we need to learn how to integrate odd powers of secant and even powers of cosine. I'm going to start with the odd powers of secant. So we need a starter set odd powers of secant. We're going to start with integrating secant to the first. Remember, this is without tangents. If we have even powers of tangents and an odd power of secant, that's just more odd powers of secant. If we have odd powers of secant and odd powers of tangents, then we have a substitution problem. So this is specifically odd powers of secant, no tangents. So we need a weird technique for integrating secant on its own. We need to first learn the integral of secant. We need to learn that the integral of secant is the natural log of the absolute value of secant theta plus tangent theta. Once we learn how it works, we don't have to do it anymore. We can just remember that the integral of secant of theta to theta is a natural log of the absolute value of secant theta plus tangent theta. I know, obviously, right? Everybody's thinking, yeah, I don't know why we're going through all this. It's obviously that. The integral of secant theta d theta is obviously natural log of absolute value of secant theta plus tangent theta plus c, of course. And it's so obvious that that's the case because all we have to do to figure it out is multiply by 1. So first things first. Let's be practical. And let me just tell you that the integral of secant theta is the natural log of the absolute value of secant theta plus tangent theta plus c. Step one, know that it's this. Step one, just remember this. If you're engineering, you can stop. All right, I know it. Let's see how this works. So engineering majors, don't worry about this. Math majors, you want to know how things work. So let's talk about how things work. All we have to do is multiply by 1. And here I'm telling you exactly what we're multiplying by when we multiply by 1. That's one of the great tricks of mathematics. Multiply by 1. If you get stuck, multiply by 1. Or add 0, or just change your variables to drop down to an easier problem. Our technique is going to be multiply by 1. Actually, even before we do that, now that I've put it in your mind that our technique is going to be multiply by 1, clearly I'm not just going to stick a 1 on there because that's boring and it doesn't do anything. We're going to multiply by 1 in a special form, like getting a common denominator. We're going to multiply something on the top and the bottom, the same thing on the top and bottom. That's going to be multiplying by 1. And since we know we're multiplying by 1, that is multiplying by the same thing on top and bottom, we can now see what the top and bottom needs to look like. Maybe we don't see it yet. What's the derivative? Let's see that the derivative with respect to theta of the natural log of absolute value of secant theta plus tangent theta. Let's take the derivative of this function. Let's see where this shit comes from. The derivative of natural log of a thing is 1 over that thing times the derivative of that thing. The derivative of natural log of something is 1 over that thing times the derivative of that thing. So I do 1 over secant theta plus tangent theta times the derivative of secant theta plus tangent theta. The derivative of secant theta is secant theta tangent theta. And the derivative of tangent is secant squared. Now notice in the numerator, I have a common factor of secant theta. I never fit this on one line going this way. I know, just like in 20 years of doing this class twice a year, I always run out of space when I do this. Like before I started writing, it's like, oh, dude, you got to move it over. I wrote the d over d theta here. I'm like, oh, dude, it's got to be over like 1 more square. I'm like, oh, it'll be fine. I'll just write thinner. And I don't write thinner. And I know it's not. What's wrong with me? Seriously. Notice that we have a common factor of secant in the numerator. And that leaves behind a secant theta. Oh, I'm going to write it in the order here. leaves behind a tangent theta from this term and a secant theta from this term. And in the denominator, I still have secant theta plus tangent theta. And there's the factor of 1 that we're going to use. We're going to multiply on top and bottom by secant theta plus tangent theta over secant, I said top and bottom. We're going to multiply the top and bottom by secant theta plus tangent theta. That is, we're going to multiply by secant theta plus tangent theta over secant theta plus tangent theta. Here is our 1. So our technique is going to be to multiply by 1. And here's the 1 that we're going to multiply by, secant theta plus tangent theta. Now, when we look at the integral of secant theta, is d theta is natural log of absolute value of secant theta plus tangent theta. Now we can see, yeah, obviously, because all we have to do is multiply by 1. Because if we take the derivative of what we're saying the integral is, that's what happens. So let's see that in action. So we're going to start with our integral of secant theta d theta. And we're going to multiply the secant theta by 1, but this special form of 1. We multiply out the numerator. On the top, we end up with secant squared theta plus secant tangent. And now we can see the substitution. W is going to be that denominator. Makes sense, because when we integrate this, we're going to get a natural log of absolute W. And up in the numerator, that's our dW. Now it's a substitution problem. If we want to make the substitution, W equals secant theta plus tangent theta, then I need a factor of dW to be secant theta tangent theta plus secant squared theta to theta. And that's what we have in the numerator. So our integral is just 1 over W dW. The integral of 1 over W dW is natural log of absolute W plus C. I need another line anyway. I'm so precious about space. How's that, right? One whole page of notes, like 7 minutes dedicated to just something that we have taken care of in the top line of this problem. Step one, just remember this. Just remember that the integral of secant theta is natural log of absolute value of secant theta plus tangent theta. For higher powers of secant, do parts. Remember this, and then do parts. Throw in all the caveats. For higher powers of secants, we'll just use parts. Specifically, for higher odd powers of secants, so 3, 5, 7, etc. And specifically odd powers of secants without tangents. Specifically without odd powers of tangents. I don't want to get actualities when I just say on higher powers of secant. Here's one that came up yesterday, and it's the next odd power of secants without odd powers of tangent that will come across. My suggestion is that we use parts. So we're going to use parts. I should warn you ahead of time, there are going to be two sides of the equation shenanigans for this particular integral. What's going to happen is that once our secondary integral is going to have another secant cube that we're going to move over to this side and then just divide by a constant. So weird shit going to happen, be warned. So for parts, we need to identify a u and a dv. The important thing to remember is that dv has to be something we can integrate. So let's say if u so the dv has to be something that we can integrate. Now let's be careful because we do know the integral of secant of theta. Here are our options. I'm going to start with a couple options that aren't going to work like this. This one sucks. I don't like this one because this just dropped a theta into my product of powers of trig functions. Ugh, that makes things worse. So doing this will drop a theta into our secondary. No. Let's try something better. Where I think, well, we just learned the integral of secant, so I know I can put the secant in the dv location. Then when we integrate, now the integral of secant is natural log of absolute secant theta plus tangent theta. And at this point, it's like, well, we just introduced a natural log into our secondary. So also, no. I know it's really exciting to take this new piece of information and try to use it immediately, but this is not a video game. We're going to need a key in this next room. Or we just found a key in room A. Oh, look, a lock in room B. I wonder if they're related. So we're going to change things one more time. Let's say U is secant theta and put dV as secant squared theta. This one is going to work out much better. If U is secant, if U are secant theta, then du is secant theta tangent theta. That's still the form that we like. It's a product of powers of trig functions. And V is just tangent theta. Now, this is something we can really get behind. Because now our secondary integral is just product of powers of trig functions, and we like that. So our integral of secant cubed theta is going to be UV minus the integral of v times du. Now the v times du is going to give us tangent squared. So it's secant tangent squared theta d theta. So now our secondary integral is secant theta tangent squared theta, which is just more odd powers of secant. That tangent squared can be replaced with secant squared plus 1. And we're going to end up with a combination of secant and secant cubed, a sum of secant and secant cubed. So just quickly, I'm not going to be able to finish this out. Our secondary is going to involve a secant cubed and a secant theta. Secant theta, we know the antiderivative of. The secant cubed is what we started with, so we're going to put that on the other side. Now we'll just have 2 copies of integral of secant cubed theta. That's going to be our strategy. I'll finish writing that up in the notes and post that on the Canvas. And then we can talk about it next week if we need to. That's going to do it for today. I will see you all. Oh, that's going to do it for this week. I will see you all on Tuesday because it's the 4-day weekend. Everybody have a good weekend.